So our second speaker is Jim Gatheral. Jim is Presidential Professor, a wonderful title I think, at Baruch College of the City University of New York. He was previously Managing Director at Merrill Lynch, where he led the Quantitative Research Group for 17 years. He's the author of the best-selling The Volatility Surface, a Practitioner's Guide. One of his students once paid him what I think must be the ultimate compliment for a university teacher. The student thanked Jim for helping him to sound smart at an interview. So I'm planning to listen very carefully to what Jim has to say to see what I can pick up.
Okay, well, thanks very much for that too kind introduction. And of course, thanks for inviting me here. I'm quite overwhelmed by the beauty of the lecture theatre. I don't think I've ever spoken at a place quite this upper class. Okay, so I've got many slides as usual, and so I'm going to rush my way through them, hopefully giving you a flavour of what this is all about. So, rough volatility, hopefully that will be self-explanatory once we get to the pictures, is joint work with a bunch of different people who are my co-authors and their students. Okay, so here's an outline of my talk. We're going to look at the volatility surface, and we're going to look at the time series of historical volatility, and we're going to see that they have a connection. And in fact, we're going to see some beautiful regularity in the time series of historical volatility. And let's try not to get confused here. So we're going to see a remarkable monofractal scaling property of historical volatility. This leads to more or less, I would claim, a unique model of volatility under P, the physical measure, and then we do change of measure to be able to do option pricing. And of course, there are many things you could do there, but the simplest choice of the measure change gives rise to a very simple model under Q, which appears to fit the volatility surface that we observe extremely well. Then, as one application, we can forecast the variance swap curve, so I'll talk very briefly about that, and then I'll spend a little bit of time talking about calibration, which is still an open problem. Well, it's not an open problem in the sense that we can do it, but we can't do it in a reasonable amount of time. Okay. So here is a volatility surface. It's a very famous volatility surface because it's the one in the book that you referred to. So what's interesting about this? Well, two things are interesting about this. One is the observed volatility surface is a beautiful shape. And I would argue that volatility surfaces that are generated from conventional stochastic volatility models don't have such a beautiful shape. And if we take any slice through this volatility surface, in other words, we look at one individual volatility smile, there's not much you could say about the underlying dynamics that gave rise to that thing. Basically, all we could say is that on the one hand, we don't know what the volatility is going to be over the life of the option that we're trying to hedge. This is clear. And on the other hand, you can say, well, if the stock price goes down, the underlying volatility is also, likely to go up. But however, there is one feature of the implied volatility surface that does give us quite a bit of information about the underlying dynamics. Instead of just looking at one volatility smile, we can look at the whole sequence of volatility smiles labeled by time to expiration, and specifically this statistic, or this feature, the term structure of implied volatility skew at the money, which I define to be the derivative with respect to log strike at the money, log strike equal to 0. This is very sensitive to the choice of volatility dynamics in a stochastic volatility model. So let's take a look at the picture. For that particular day in history, we see that the term structure, now I have to keep myself organized. We see that the term structure of implied volatility skew was almost a perfect power law. Now, if you were to ask a trader, what is the term structure of implied volatility skew, he would say it's 1 over root t. And you would ask him, why is that so? Well, he said, well, everything is measured in standard deviations. Well, that's a good heuristic, but it turns out if you look more carefully, it's not actually 1 over root t. It's actually a little different from 1 over root t. The exponent is a little bit less. On this particular day, the best fit is an exponent of 0.44, and on any other day, it could be anywhere between 0.3 and 0.5, typically. Okay, so it's a stylized fact that when you look at the vol surface on any particular day in history, we see that the term structure of implied volatility skew looks like a power law, and 1 over t to the alpha, and alpha can be somewhere between 0.3 and 0.5. So that's the first motivation for rough volatility, is to have a stochastic volatility model that better fits the observed implied volatility surface. So it's well known, of course, that the conventional stochastic volatility models don't generate this term structure of implied volatility skew. In fact, what they generate, if we go back to the picture, is something that's pretty... I get so confused with this right now. Laser. It generates something that goes as 1 over t, not 1 over t to the alpha for long dates. So for long dates, it's wrong. And for short dates, it's wrong because it goes to a constant. And in between, it's a decaying exponential. So it's quite different from what we observe. So the conventional solution is just to keep adding factors. Each time you add a stochastic volatility factor, you add another decaying exponential to the term structure of volatility skew, and you forget that it's constant at the front and 1 over t at the back because you keep squeezing the range by adding factors. Right, so now let's make this a bit more quantitative. There is a nice expansion, asymptotic expansion of the implied volatility surface that was devised by Bergomi and Guillon. And essentially what they say is that you can approximate the implied volatility for any log strike and expiration by at the money vol plus a second order term, which is basically skew, plus a first order term, which is basically skew, and a second order term, which is basically curvature, and then you can keep on going in principle. In their paper, they go to second order. We only need the first order term, and we can see that the first order term, W, is essentially the variance swap. CXI, they call the spot vol autocorrelation functional. And we can see that if you have your model written in forward variance curve form, well, what's the forward variance curve? It's basically the derivative of the variance swap curve with respect to time to maturity. So these things are tradable instruments, not just in theory, but in practice. It's the risk-neutral expectation of the instantaneous variance at some future date u, given the information that we have at time t, which is today. So assuming that you have written your model in that form, that means you have dynamics for the log spot, you've written them down. You have dynamics for the forward variance curve, you've written those down. Then this thing you can compute, and now you do your double integral, and you can compute this thing. So you see we have now a one-to-one mapping between the model and some approximation to the implied volatility. So if you observe this, you can say something about that. And if you know this, you can say something about that. So now if we take as a perfect example, as a prototypical example of a stochastic volatility model, we take Bergomi's own model, which where he says that he has a log normal model, where he says that essentially the log of the forward variance is a sum of Ornstein-Uhlenbecks. So these eta i's are vols of vol, one for each factor. These kappa i's are mean reversions, one for each factor, and the I labeling the factor. So typically you would have n equals 2, but maybe you have n equal 3 or more. Then you get a term structure of volatility skew that looks like this. Okay, so now we started with a beautiful power law that physicists would love, and using our prototypical stochastic volatility model, we end up with a sum of decaying exponentials, which is just not cute. It looks pretty ugly, right? So we would like to have something cute. And what was the origin of the ugliness? Well, it's clear that the origin of this ugliness was doing a double integral of this exponential kernel. So ideally, we'd like to rip out this exponential kernel and replace it with a power law kernel, and then we generate something here. But if we were to do that, what would we have? We would have something that looks like that the log of the forward variance is just fractional Brownian motion, something like that, for those of you who are familiar with fractional Brownian motion. Okay, so that's the first motivation, better fitting stochastic volatility model. The second motivation for rough volatility is to do with properties of the historical time series of volatility. Well, what do we mean by that? I mean, instantaneous volatility, of course, cannot be observed, but what we can do is we can estimate integrated variance over 1 day. And that's pretty easy in principle because we have lots of great estimators that have been devised by various statisticians. And we've got lots and lots of data, typically like 100,000 trades each day in an index. But the practical difficulty, of course, is cleaning the data. Now, we're very lucky. This has been done for us by a competitor hedge fund in collaboration with Oxford. So the Oxford Mann Institute publishes for like 21 different indices. They claim it's more, but I found 21. And make these, so they make estimates using a bunch of different estimators of integrated variance each day since the beginning of the year 2000. They update this pretty much daily. And so all clean, so you get beautiful time series of some kind of approximation to instantaneous volatility. If you're willing to accept that integrated variance for 1 day is an approximation to instantaneous vol. So what do we get? Well, this is S&P from 2000 to 2016, and of course the obvious feature of this data is the crash of 2008, when we all were worried that the financial system would completely collapse. So one thing we want to do is to measure the roughness of the historical volatility time series, and the specific quantity that we're going to look at is a kind of moment. So we're going to look at the difference between the log of the vol at some date today, delta days from today. It could be 5 days or 20 days or 100 days or whatever. Subtract off the log of the vol today and raise that to the power q. So for example, if we had M2 delta, this would be like a sample variance of lags at lag delta. And when we plot this on a log-log plot with log of delta on the x-axis and log of MQ delta on the y-axis, then we get the thing that appears in all econophysics papers. We get straight lines on the log-log plot, which tells us what? Well, it tells us that MQ delta here is equal to something times delta to the power zeta of q for some zeta of q. Now, typically this zeta of q is a complicated function of q in a typical model. However, in this data, it's an amazingly simple function of q. Zeta of q is directly proportional to q. So what this tells us is that we have monofractal scaling. From the plot, we see that for each q, m is proportional to delta of zeta q, but zeta of q is just q times h, with h roughly 0.13. This is the same scaling that we see in fractional Brownian motion. Now, of course, instead of looking at instantaneous variance, which we can observe, we're looking at integrated variance. So this thing is going to bias our estimates of h high. On the other hand, the estimators are noisy, so that's going to bias our estimates of h low. And so we need other tricks to try and find out what h actually was. And many people, including Miko here, have come up with tricks to figure out what h actually is. So now we can use this methodology, these methodologies, to estimate h, the time series of h. I mean, one obvious question is, was h constant over the period from 2000 to 2016? And it's pretty obvious that it wasn't. Now, here's another interesting thing that happens when you draw this picture, which was incidentally copied from a Miko paper by one of my students. Not actually copied, but replicated is the right word. But the nice thing about this picture is you might wonder, well, if you estimate h over the whole period, you maybe get, and you're more careful because remember it was biased high and it was biased low. So let's say h is 0.1. Just wave our hands and say h was really 0.1. Was it constant over that entire period? And you look at this picture and you say, well, the estimates are so noisy, maybe it could have been constant. But when you look to see where the peaks are, you see the peaks correspond to real financial events, right? The Lehman bankruptcy, the flash crash, the Greek debt crisis, the Brexit vote. So we see that when h goes up, it tends to be correlated with some real financial event. So this gives us confidence that when we see h moving up and down, it really corresponds to something that's going on in the underlying data. And it's not just noise in the estimate. And we also see that when the market is calm, h seems to be pretty close to zero. Okay, so now we saw this beautiful scaling relationship from the moments. How do the histograms look? Well, amazingly, the log of the vol looks to be Gaussian. Now, what are these red lines and blue lines? The red line is just the Gaussian distribution fitted to the histogram with the same mean and standard deviation. And the blue lines are simply the red curve from day one dilated by delta to the power h. So we see that not only do we get beautiful scaling of the moments, but the histograms themselves scale. And we can do this for all the indices, and we get very similar results. And thanks to Miko and his co-authors, we see that, in fact, well, let's put it this way. I haven't heard of a single underlying for which the scaling is not observed. So in the paper, we redid it for DAX and Bund. I had a student who did it for gold and crude oil, although for crude oil, the histograms don't look Gaussian anymore. They have fatter tails. And then Miko and his co-authors, they estimated volatility time series for more than 5,000 individual US equities, like 5,700 or something, plus ETFs. And they found rough volatility in every case. So same kind of results. So it seems to be universal. And one question is, why do we observe this kind of universality? And we'll have an explanation for that in a couple of slides, a potential explanation. But if we take these three things together, the beautiful scaling, continuity of the volatility time series, well, that's a question of taste. Many people believe in jumps. We can talk later about why one should not introduce jumps, but one can't distinguish between continuous time series and a jumpy time series. It's impossible. But let's just suppose that the time series of volatility is continuous and that we see these beautiful Gaussian distributions with the right scaling. If you believe all that, there's only one possible model that you can write down, which is kind of cute. Now I've pressed the wrong button again. Only one model that you could write down, which is essentially that the log of the vol is some constant times fractional Brownian motion. And this is also, of course, ignoring the fact that h appears to move over time, but assuming h was constant, there would be only one model that you could write down. Now, what is fractional Brownian motion? For those of you who don't know what it is, it's a generalization of Brownian motion. Obviously, and you get conventional Brownian motion back with h equals a half. So you can see that very quickly here. If you put h equals a half and suppose that t is greater than s, then you're going to get t plus s minus t minus s. You get 2s divided by 2, which is s. It's the conventional covariance structure of Brownian motion. If h is greater than a half, you get a time series that traders would say is trending. And if you get, if h is less than a half, then increments are negatively correlated. And so trader would say mean reverting. And if h is very small, close to zero, as it appears to be from the data, then the volatility time series is basically doing this. And we all know this. When we draw a volatility time series, it looks incredibly rough. And probably we look at that time series and we say to ourselves, well, that's because the observations are noisy. But if you think about it, the observations are not actually that noisy because we've got lots of data now. And the error in each of these daily observations, it's not that big. Right, so here is the real time series of realized volatility, well, square root of realized variance, to be more precise. And here is one that's generated from a simulation. And I'm going to skip the slide quickly because when I say they're the same, everybody, there's always somebody who complains they look quite different. But the point is, they appear to be as rough as each other. And they are same order of magnitude. So the simulation seems to look, and we have periods of low vol, we have periods of high vol. Everything looks kind of similar between the model and the data. So I claim that the qualitative features of simulated and actual graphs look very similar. We have persistent periods of high volatility alternating with periods of low volatility, very rough sample paths. So this is one of the reasons it's called rough volatility. And on closer inspection, we observe the well-known fractal type behavior, by which I mean that if we look at the graph of volatility over a month or over a day or over a year, if they're not labeled, it's pretty hard to tell them apart. And now we see an explanation. The explanation is simply that in order to get from a graph, for example, for 1 month to a graph for a year, we're going to dilate that graph by 12 to the power h. But h is such a small number that this is basically the same plot. Now, where does this universality come from? Well, according to one of my co-authors, Matthew Rosenbaum, he has a very cute story to tell. According to his story, this universality comes from order flow, in other words, from market microstructure. It's well known that order flow is highly autocorrelated. It has a long memory property. So as we start with a process where buys make the price go up and sells make the price go down. So far, sounds very plausible. And buy orders stimulate more buy orders and sell orders stimulate more sell orders. And then the question is, how does this self-exciting process, how does the excitation decay? And if you assume that this excitation decays as a power law, you end up with a model that looks very much like the rough volatility model, except you have a square root of v in the integral. This is, in fact, a natural generalization, a natural fractional generalization of the Heston model, the well-known Heston model. And we can relate the parameters of this fractional generalization of the Heston model to the parameters of the microstructure model that gave rise to it. The correlation rho is related to liquidity asymmetry. In other words, the fact that buy orders have more, sell orders have more impact than buy orders, at least in the model. And this parameter here is related to the endogeneity. So in order for this limit to work, you have to believe that most orders in the market are between market players and not end users. So most of the activity in the market is completely endogenous, and I certainly believe that. When I first started trading, I was shocked to see how much trading in the foreign exchange market was between market participants and nothing to do with end users. Okay, so now amazingly, they were able to find the characteristic function for this fractional generalization of the Heston model. And this is how it looks. It's completely, again, it's just a fractional generalization of the conventional Heston model. And given that the Heston, well, why do people use the Heston model? It doesn't agree with the time series. The vol surface that it generates doesn't look like the vol surface that we observe. The reason people use it is because it's highly tractable. And so this one is almost as highly tractable as the conventional Heston model. In the conventional Heston model, this function h is got by solving a Riccati ODE, which can be done in closed form. In this case, it's got by solving a fractional Riccati ODE, which has to be solved numerically, but you can do it with standard techniques. Okay, so now we have our pricing model under P. I claim that the model that you can pick under P is pretty much uniquely specified by the data. What does the model look like under Q? Well, this is our model under P. In order to get a model under Q, we're going to do a change in measure. But first of all, let's talk about pricing. In order to do pricing, we need to look at the difference between the log of the variance at some future date u and the log of the instantaneous variance today. And I'm going to split it. So, well, I better explain what this is. There are many, many possible representations of fractional Brownian motion in terms of Brownian motion, but the one that we're going to be interested in looking at is the one that starts from minus infinity. Why minus infinity? Well, because if you choose any other date in history, you're going to discover that that model is going to refer to that reference to the historical date is going to keep coming out. It's basically very undesirable. There's only one unique date in history, and I claim it's the Big Bang. So I'm going to call minus infinity the Big Bang. And obviously, this means that's probably the reason people didn't look at these models in the past, because when you write a pricing model in terms of the history of the Brownian motion since the Big Bang, then we say, well, this is not very practical. But it turns out it all works out. You will see in a second that it all works out nicely. So now let's rearrange this. Instead of writing the two integrals in the way we wrote them in the previous slide, we're now going to split it into a piece that we don't know, which is the evolution of the Brownian motion between today and the future time u, and the information that we supposedly already have. I mean, even if we got it, it's kind of unlikely we'd know what to do with it, but imagine that you have the history of the Brownian motion, in other words, the history of the evolution of the S&P since the Big Bang up to the present time. And so we have two terms. One is a martingale in T, and the other piece is adapted to the Brownian motion, adapted to the filtration. So if we were just pricing under P, and remember much of the literature is like this, it just says P equals Q. So if we were to suppose temporarily that P was equal to Q, which I don't believe, then in that case, we would have a model that looks like this. We would have that the log of instantaneous variance is just some constant times something that looks like fractional Brownian motion, but it's not quite the same. It's fractional Brownian motion with all its history chopped off, and then the history piece. But now we notice, this is the trick. Now we notice that this can be trivially rewritten as the expectation of instantaneous variance times a stochastic exponential. So if I were to know this, I would also know that. Now, if P equals Q, we recognize that this is just the forward variance curve. So in other words, if I can observe the forward variance curve in the market, which I certainly can, then somehow this forward variance curve is giving me all the information about the history of the Brownian motion that I need to be able to compute the prices of options. Okay, so how do we price under Q? Well, we need to change measure. And so, in general, this change of measure could depend on anything. It could depend on people's mood. It could depend on weather in Miami. It could depend on anything at all. In practice, we know it's got something to do with the level of volatility, because if this, for example, if this lambda sub s were deterministic, then in that case, our model for volatility would be log normal. And then were we to look at options on VIX, we would see that those smiles would be approximately flat. Now, when we look at options on VIX, we see that, on the contrary, VIX smiles are strongly upward sloping, which means that this lambda s has to be big in high volatility scenarios and small in low volatility scenarios. But this is too complicated for us now, so we're just going to ignore all that, and we're going to do deterministic change of measure, because it will turn out that if we do deterministic change of measure, we still get something that's highly tractable and fits the volatility surface very well. So if we do that, then if we do that, now this change of measure gives us an extra piece. If we combine this, well, how do we interpret this now? This is essentially an optimal forecast of a instantaneous variance under P, and I'll show how to do that in a couple of slides, times a factor that depends on the price of volatility risk. So this is totally intuitive, right? That the forward variance curve should have two components. One that is something to do with forecast of variance in the future, and the other piece is to do with price of volatility risk. And then again, we have the expected stochastic exponential, which, by the way, looks exactly like the Bergomi model. In fact, it's exactly the Bergomi model with those nasty exponential kernels replaced by a single power law kernel. So this and that's why we call it a Rough Bergomi model, by the way. I probably said that here somewhere, yeah, in the title. This is why we call it a Rough Bergomi model, because it's formally identical to the one that Bergomi wrote down, but with a different kernel. Now, this one is non-Markovian in the sense that option prices don't just depend on the spot and the instantaneous variance. They depend on the entire history of instantaneous variance, or equivalently, they depend on the entire forward variance curve, which is an infinite dimensional object. So it's Markovian in this infinite dimensional state vector. And we've achieved our original aim of ripping out that exponential kernel and replacing it with the power law kernel. Okay, so now what about the stock price process? The beautiful thing about what we did so far was we basically just looked at a picture, or looked at a bunch of pictures and said, look, the only process that we can write down for the volatility is this one. We would like to do the same thing for the spot. Unfortunately, we can't figure out how to do that. So we cheated and just said, well, let's just do it the usual way, the way everybody else does stochastic volatility. So we write Black-Scholes, ds over s is the square root of the variance times dz. And we allow this variance to move around according to our rough volatility process. Now, what about simulation? Well, in our pricing paper, we did an exact simulation, which was horrendously slow. And then Mikko again and his collaborators came out with a much more efficient scheme. Sadly, still not efficient enough to do effective calibration, but much more efficient than the scheme that we wrote down in our paper. Okay, so we're not really at the stage where we're able to calibrate the parameters, but is that a disaster? Well, it's not a disaster because we can actually just guess the parameters. If you think about it, there are only 3 parameters in this model. H, which we said was around 0.1, the vol of vol, and the correlation between vol moves and spot moves. And the question is, can we guess them just by looking at the volatility surface? And the answer is yes, we can. H controls the decay of the at-the-money skew for very short expiration. So we do a log-log plot of the at-the-money volatility skew, like the one I showed you earlier, and we can estimate H. Just like every other stochastic volatility model, the product of the correlation between vol moves and spot moves and the vol of vol sets the level of the skew for some longer expiration. So we could pick 1 year, for example, whichever one we happen to know. And then if we know this product, which we claim to already do from that level of the skew, if we keep this product constant, but we make rho more negative, then essentially what that does, if we fix the smile now, we imagine we have a smile, and we make rho more negative, then what this does is it pushes the minimum of the smile down and to the right. So we just take one smile, and we fiddle around with the correlation, keeping this product constant in such a way as to fit that particular smile. Well, now I'm going to show you one particular date where we just guessed the parameters. The guessed parameters were H equal 0.05, vol of vol of 2.3, and very negative correlation between vol moves and spot moves. And here's the picture. And despite the very high quality of the Winton projector, I think you're going to have difficulty telling the difference between the data and the fit. So for example, here we have the red points are bid implied vols, the blue points are offered implied vols, and the orange line is the fit. So all these orange lines come from the same three parameters. It's not like we're changing the parameters for each slice. The same three parameters, H equal 0.05, vol of vol 2.3, and correlation minus 0.9 give you all of the slices. Well, you could argue except the front one, but this one had only 1 day left to trade, so let's not complain too much. One very interesting thing about these pictures, I think, is that we have generated the extreme short-dated smile that's often commented on in the literature without jumps. All the processes here are continuous. The stock price process is continuous, and the volatility process is continuous. So in some sense, the distributions that are generated by this rough volatility process, because remember, volatility is very spiky, are jump-like, but there are no jumps. And of course, I've got to show off how beautiful this is. I just took the best one. You can see those bid vols and offer vols, and remember, this is just a guess. There was no calibration here. We just guessed the parameters. Okay. Now we can look at the money vols and skews. At the money vols, in principle, depending on how quickly we can calibrate. So when I showed this picture originally with our horrible Koleski exact scheme, it was impossible to get this exact. But now with the more efficient hybrid scheme, it's faster to iterate. And so basically we iterate on the input forward variance curve until we match the at-the-money vols exactly. So these little green dots are the model and the blue dots are empirical. So they should in principle match exactly. So that's no surprise because the forward variance curve is the input object. But however, this is interesting. The blue points are non-parametric estimates of the volatility skew on that particular day in history, and the red line is the model. So, you would think this is just some stupid functional form that we fitted to the vol skew, but no, it is the model. So very impressive fits. So what can you use this for? Well, you can use it for a number of things, but one obvious thing that you can do with this model is to forecast a future implied variance. Miko, again, with his, he's been extremely busy with his co-authors, and he shows, in fact, that this is a very efficient forecast of future, much better than Garch, for example, which is not even in the running. But I would say a close competitor is probably Fulvio Corsi's HAR estimator. But anyway, we end up with a very, very efficient estimate. It's well known how to forecast fractional Brownian motion. That comes from communications literature. And this is the well-known forecast for fractional Brownian motion. And you can see it depends on the history of the process from the Big Bang up to the current time. And this history is decayed at something like 1 over root t, depending on how far forward delta you're forecasting. So we have a power law kernel, and you have to go far back in history. Your forecast is going to depend on everything that happened in the past, in principle. However, we're not interested in forecasting fractional Brownian motion. We're interested in forecasting the exponential of fractional Brownian motion, and so we need some kind of convexity adjustment, which appears here. And so this can be done, and Mikko and his co-authors confirm this forecast outperforms the best performing existing alternatives, at least at daily or higher timescales. So they say that their thing does better within a day, but I don't care about within a day, and I'm an option trader. I don't have 1 hour options yet. So we tried calibrating this thing, and we have been successful according to some measure of success. I'll explain that in a second. So we've investigated, for example, asymptotic expansions, Chebyshev interpolation, which actually did work in moment matching. We can't really claim to have a real success, but now let's give a little more detail on the Chebyshev thing. So the idea here is we've only got 3 parameters, right? This is the key thing. We've only got 3 parameters. So now let's compute the objective function on a 5 by 5 by 5 grid. So we've got 125 computations of basically the distance between the model and the data. Why is it so slow? Because after all, we've got a wonderful numerical scheme from Mikko and his buddies. So why should this be so slow? Well, the reason is simply that we need very high accuracy in order to be able to resolve the minimum. If we don't have millions of Monte Carlo paths, we basically can't see the minimum. Now, if we do have millions of Monte Carlo paths, the minimum is quite evident. So it's not like the minimum doesn't exist. It's not like we have a surface with multiple local minima. It's really there, but that's the reason why it's so slow. So how long does this take? I don't know if I wrote it in the slide. Yes, I did write it in the slide. It took us 2 hours running in parallel on 32 CPUs. Of course, that was in R, not in C, so maybe we'll do better if it's properly written in parallel in C, but I don't think it's going to do that much better. So it's still not ready for industrial application. So another idea, more conceptual, which appears still not to work for other reasons, which I'll explain, is to find some quantity which is easy to compute in the model, which can also be observed in the market. So an example might be the variance swap. A variance swap, it can in principle be observed from the smile and is easily, in this case it's a model input, but in a typical model it would be a model output. Well, it turns out that there is such a quantity and it has some beautiful properties. So a few years ago, Elisa Alos came up with a beautiful formula which allows you to decompose an expectation into originally 2 pieces in her Mariavin decomposition, but we're going to use the Ito version, which she came up with in 2012. And I explain briefly how you get this. So you imagine that you have a model for the log of the spot. Well, it's the usual one. And you imagine that you have some function f which solves the Black-Scholes equation. Well, what is the Black-Scholes equation? It just says, so you think of W as being total variance or something. So we're going to take it to be the expectation of the integral of instantaneous variance over the life of the option. That's the natural thing. And all the Black-Scholes equation basically says in that case is that the gamma of the option, this is the gamma of the option in terms of the log spot, should be equal to the vega. So you have some function f that satisfies this Black-Scholes equation, and you have the log of the spot evolving according to the usual thing, Black-Scholes, essentially, with the vol, of course. The vol, of course, could be anything. So we specify W, which is the variance between now and the end date of the option, to be the integral of the instantaneous variance. So it's the variance swap. More specifically, it represents the value of the static hedge portfolio for a variance swap, and it's a tradable asset. So it can actually be traded. And for each U, the forward variance is a martingale in T, so we can write down the dynamics of this variance swap. It consists of two pieces, basically the instantaneous variance that you realize today, plus a martingale piece, which refers to the variance that has not yet been realized. And then according to this decomposition formula, the expectation of F splits into three pieces. The piece that you know today, you could call it intrinsic, something to do with the covariance of the spot and the vol, because remember, M is to do with the dynamics of the variance swap, and X is to do with the dynamics of the log of the spot. And then the covariance, the covariance between the vol and the vol. Now, this looks very similar to the Bergomi-Guillon expansion, and in fact, these terms turn out to be exactly the same in some sense. So we'll adopt the following notation for the Bergomi-Guillon autocorrelation functionals. So here we have, again, the spot-vol autocovariance, and here we have the vol covariance. So let's just change the notation from their paper at this point. Now, suppose that we consider the following definition of F. It's x squared plus w times 1 minus x plus a quarter w squared. Well, why would you want to look at that? Well, it solves the Black-Scholes equation, so the decomposition formula applies to it. And it's easy to compute the derivatives of F. We plug it into the decomposition formula, and this magical thing occurs. Look what we get. We get that the expectation of the log spot squared minus the expectation of the log spot all squared, which is the variance of the log spot, is equal to the quadratic variation, which is the fair value of the variance swap, plus two extra pieces. And those extra pieces are the spot-vol autocorrelation functional and the vol-vol autocorrelation functional. Now, why is this interesting? Well, we're going to call this quantity here stochasticity. Why do we call it stochasticity? Because, for example, in Black-Scholes, that thing would be 0. In a simple jump model, that thing would be 0. In a stochastic vol model, as you increase the vol of vol, this thing is going to increase in general. So this thing on the left-hand side, well, what is W? It's the variance swap. It can be computed from the smile. This thing is basically the expectation of the square of the log spot, and that thing can be estimated from the smile. There are basically option strips that correspond to the fair value of both of these things on the left-hand side. And on the right-hand side, this thing is easily computable from the model if the model is written in forward variance curve form. Virtually any model can be written in forward variance curve form, and certainly the rough volatility model can, so we can do it for that model. We're doing well. So just to summarize, this thing we can get by looking at the option market, and this thing we can get from the model. So ideally, we just compare the two and minimize the distance, and we get the model parameters. Now, there's a beautiful formula, it turns out, for stochasticity. You may or may not be familiar with the beautiful formula for the variance swap in terms of the smile. If we obviously, everybody typically writes down the smile in terms of the log strike, little k. But we could reparameterize the smile in terms of z, d2 in the Black-Scholes formula, which is we get from the market. if we were to represent it in, if we were to reparameterize the variance, the implied variance in terms of D2, we would have this amazingly beautiful representation for the variance swap. It turns out we can do a very similar thing for stochasticity. It has two components. One thing you might call the skewness of the smile, and the other thing you might call quarticity of the smile. So now, if I give you a functional form z for the smile, computing this is trivial. There's a practical problem, though, and that is that in contrast to the case of the variance swap, where the contribution to the integral mostly comes from strikes that we can observe close to the money, where z is approximately 0. If z is approximately 0, there's no contribution to either of those terms, which means that all the contribution comes from out of the money strikes, and sadly, the market doesn't cooperate with us. These strikes are not really observable. As an example, I'm going to skip the example, except to say that in the Heston model, everything can always be computed in closed form. Anything interesting can be computed in closed form. We can compute the left-hand side, we can compute the right-hand side, and it's no surprise that they are the same. Some horrible expressions that we don't really care about. More interestingly, we can also compute these quantities in the Rough Bergomi model. They're complicated things that you can look at later. And so now we can look to see, does this work in practice? Well, with Heston, everything always seems to work. Unfortunately, Heston is not the model of the market, is not a good model of the market. So what I've done here is I have compared some kind of rescaled measure of stochasticity. So I've taken 1 day in history. I've kept all the strikes and expirations. I ripped out the option prices and replaced them with fake Heston prices and asked myself, can I calibrate the parameters of the Heston model from this fake Heston market? And the answer is yes. It works really nicely. The red are points from the left-hand side, in other words, estimating using the option strips. Where they're off the curve is just because for that particular expiration, there were too few strikes to be able to resolve the quantity that we're trying to estimate. And the blue line is the closed form formula that I projected up on previous slides. And, okay, so now we can now here is the ugly one. If we do the same thing with Rough Bergomi, this blue curve, which you can see is quite different, is what we get from the model. The red points are what we get with flat extrapolation in those integrals. So if I extrapolate from the strikes that are observed to the strikes that are not observed, just flat, then I get the red points. And if I do it linearly, I get the green points. But you can see in either case, I'm unable to calibrate the parameters of the model. And if we look to see why in my final few minutes, it's really easy to see why. So my thick blue line, it corresponds to the strikes I can observe in the market. Now, of course, I can do Monte Carlo simulation of the model. So here are the strikes I potentially could have observed, but couldn't observe with the strikes that I have available. And so if I now include these strikes that don't exist in the real market, I would actually have been able to calibrate the model, as you can see here with these orange points. Now, you might ask, is there some hope that next year these strikes will be traded? Sadly not, because those strikes are so extreme, I don't believe they will ever be traded. For example, a strike of 10 in S&P that's currently trading something like 2,300, that's never going to be traded. There's no reason for it to be traded, so this is kind of hopeless. So the interim conclusion is that stochasticity is very sensitive to the extrapolation method, and there are just insufficient strikes. So if we had the magical extrapolation, which essentially means that we were able to solve the model in which we were trying to calibrate, which is kind of circular, then we would be able to extrapolate efficiently and somehow use the data that we observe to get at the parameters of the model. So it's a nice idea, but one of those things that's nice in principle, but not in practice. And here are a couple of pictures to show you. So here, is the integrand of the variance swap, and you can see the parts that are missing are really very insensitive to the extrapolation. On the other hand, if we look at stochasticity, you can see that the parts that are missing are incredibly sensitive to the extrapolation. All right, so in summary, we found a monofractal scaling relationship in historical volatility, which, thanks to Mikko and his co-authors, now appears to be universal. I mean, we always thought it was, but we had only a few underlyings, and they've got thousands and thousands of them. So this leads to a natural non-Markovian stochastic volatility model under the physical measure, and the resulting volatility forecasts are extremely efficient. The simplest change of measure gives a non-Markovian generalization of the Bergomi model, which appears to fit the observed volatility surface extremely well. Efficient calibration of the model is still, let's say, work in progress. That would be being polite. So essentially what we have here is a machine for taking high-frequency data, lots of ticks, and spitting out the shape of the volatility surface with very, very few parameters. So with that, I'm very happy to take questions.
Maybe a couple of questions.
Oh, there is some empirical evidence showing that realized volatility at different scales may have logarithmic log decay of correlation,
Right.
while your results seem to show power log decay.
Exactly. So we kind of disagree. This log decay of correlations is, if you look at the numbers, it's actually very compatible. They're both compatible. We basically just don't have data, I believe, at these very long time scales. So, in fact, Mikko, again, has done further work that allows us to more or less reconcile people's, what do we say, people believe in long memory of volatility. That's essentially what these log correlations are. So, there's no need to pick a power law kernel. You could pick a power law kernel with extra, you can make it more complicated with more parameters. And if you make it more complicated with more parameters, so long as you have that form asymptotically for very short times, we're not saying anything about what happens at longer times. So the way I would say it is, the model I wrote down is compatible with the data. You can have a model that has this rough property that is compatible with the, more or less compatible with the log correlations that people seem to believe in. But this one's also compatible. I mean, it's impossible to tell from the data, I think.
I guess I'm missing something with your calibration problem.
Yeah.
You're using enormous simulations.
Yes.
But we've got one history and we'll have one realization in the future. So I'm struggling a bit with why you've got so many orders of magnitude more work you need to do to calibrate. And probably related, if you depend very sensitively on parts of the curve that don't exist, is that the problem, that you're trying to fit things that...
All right, okay, so there are several parts to that question. First of all, when we calibrate, we're calibrating to implieds, right? So we're calibrating to the vol surface, so the history has got nothing to do with it, right? So and the problem there is that there are many choices of parameters. I mean, you can't have ridiculously different parameters, but I could, for example, pick h equal 0.05 or h equal 0.07, and they would, so long as I change the other parameters appropriately, I would get very similar shapes of the volatility surface, right? So that's why you need lots of paths in the Monte Carlo. Now, the story about stochasticity, well, this is just another possible way of calibrating the model. There, all we're basically saying is it's a nice idea in principle, but it doesn't seem to work in practice. Did I answer your question? No.
It doesn't really. As you said, there are constraints that you can put on parameters to what we can see.
Yes.
It must be
right.
Have some sensible relationship.
Yes.
And the stochasticity point is showing that the problem is things that we can't see.
Right, that's right.
Putting those two together, aren't you just exploring a very large space to try and find precise values of parameters when actually we can only ever have a rather fuzzy estimate of where
Right, okay, so yeah. I agree with you. I've basically given up. It's time to write papers. I mean, this was the point made by one of the guys at a previous talk that I gave. He said, this calibration is a waste of time. It's not interesting. Yeah. I mean, I guess the point was made when we said we can guess the parameters, right? If the true parameters are a little different, it doesn't make any difference. Yeah. Thanks.
I think it's time for coffee, so can we just thank everyone?